Introduction. You are familiar with the magnetic field around a bar magnet. The direction of the magnetic field at a point is the direction that the compass needle points. Drag the compass from the north pole of the bar magnet to the south pole. Click the next button. The direction of the magnetic lines of force is from the north pole to the south pole of the magnet. There exists a magnetic field around the Earth. Since the 11th century, sailors had been using the compass, whose needle is basically a magnet, for navigation. A magnetic field exerts a force on a moving charge. During periods of high sunspot activity, the sun emanates charged particles towards the Earth in the form of solar winds. Forces on these charged particles by the strong magnetic field of the Earth at the poles cause the charged particles to spiral down to the poles. The collisions of these charged particles with the air molecules produce light, which forms the aurora borealis, or northern lights. In this lesson, you will understand the concept of magnetic field, learn the formula for the force on a charge moving in a magnetic field. Vector F equals Q times vector V cross vector B. Use the equation F equals QVB sine theta to define the magnetic field strength B. Study the motion of a charged particle in a uniform magnetic field. Understand the principles of a mass spectrometer. A magnetic field B can be represented by lines of force. Click the back view button, then the front view button. When the lines of force of a magnetic field are directed into the plane of the screen, they are represented by crosses. When the lines of force of a magnetic field are directed out of the plane of the screen, they are represented by dots. Summary. Magnetic field into the plane of the screen is represented by crosses. Magnetic field out of the plane of the screen is represented by dots. Click on the positive charge Q to shoot it with a velocity v into a uniform magnetic field B, which is perpendicular to the plane of the screen. What happens to the positive charge in the magnetic field? Answer. The positive charge is deflected. Why is the positive charge deflected? Answer. The magnetic field exerts a force on the moving positive charge. Click the force button to view the force F on the positive charge in the uniform magnetic field. What is the direction of the force F relative to the directions of the velocity v and that of the magnetic field B? The direction of the force F is perpendicular to the magnetic field B and the velocity v of the charge. Click the Directions button and then the right-hand rule button to observe the direction of the magnetic field B, the velocity v, and the force F. Click on the positive charge Q to shoot it with a velocity v into a uniform magnetic field B, which is perpendicular to and is out of the plane of the screen. Click the Directions button to observe the direction of the magnetic field B, the velocity v, and the force F. Click on the positive charge button and then the negative charge button to shoot each of them with a velocity v into a uniform magnetic field B, which is perpendicular to and into the plane of the screen. Compare the directions of the forces on the two charges. The force on a charge Q moving with a velocity v in a magnetic field of flux density B is given by the vector equation vector F equals Q times vector V cross vector B. The magnitude of the force is F equals QVB sine theta, where theta is the angle between vector V and vector B. Test. The direction of the velocity v of a positive charge in a magnetic field of flux density B is as shown in each of the diagrams. Drag the arrow showing the correct direction for the force F on the charge into each of the diagrams. Drag the arrow showing the correct direction for the third vector into each of the diagrams in the equation vector F equals Q times vector V cross vector B. Summary. The force F on a charge Q moving with a velocity v in a uniform magnetic field of flux density B is given by vector F equals Q times vector V cross vector B. The magnitude of the force is F equals QVB sine theta, where theta is the angle between the direction of the velocity and that of the magnetic flux density B. When the direction of the velocity v is parallel to the direction of the magnetic field B, the angle theta equals 0 and the force F equals 0. What is the effect on the motion of the charge? Click the proton button and observe the motion of the charge parallel to the magnetic field. Then click the electron button. When the direction of the velocity v is perpendicular to the direction of the magnetic field B, the angle theta equals 90 degrees and the force F equals QVB, which is the maximum force. Click the proton button to observe the motion of the charge in the magnetic field when theta equals 90 degrees, then click the electron button. The equation F equals QVB sine theta for the force F on a charge Q moving with a velocity v in a magnetic field can be used to define the flux density B of a magnetic field. The magnetic flux density of a magnetic field is the force acting on a unit charge moving with unit velocity at right angles to the magnetic field. The unit for magnetic flux density B is Tesla, T. The Tesla, T, can be defined from the equation B equals F max over QV. Summary. The magnetic flux density B is defined by the equation B equals F max over QV, where F max is the maximum force on a charge Q moving with a velocity v in the magnetic field. The magnetic flux density of a magnetic field is the force acting on a unit charge moving with unit velocity at right angles to the magnetic field. The unit of magnetic flux density is the Tesla, T. The magnetic flux density is 1 Tesla if a charge of 1 coulomb moving with a velocity of 1 meter per second perpendicular to the magnetic field is acted on by a maximum force of 1 Newton. Click the play button to observe the motion of a positive charge moving with a velocity v which is perpendicular to a uniform magnetic field of flux density B. What is the path of the charge in the magnetic field? Answer: a circle. Explain why the path is circular. Answer: the force is constantly perpendicular to the direction of the velocity. Click the next button, then click the next button again. Click the deuterium nucleus mass equals 2m button and observe the motion of the two charged particles of the same charge but different masses moving in the same uniform magnetic field. Compare the radii of the circular paths of the two particles. Answer: the radius of the circular path of deuterium is twice that of proton. Click on each of the velocities, the 0.5 v button, the v button, and the 2v button to observe the motion of a proton in a uniform magnetic field. Compare the radii of the circular paths. Answer: the radius of the circular path is directly proportional to the velocity. Click on each of the magnetic field, the 0.5 b button, the b button, the 2b button, and observe the motion of a proton moving with velocity v in the uniform magnetic field. Compare the radii of the circular paths. Answer. The radius of the circular path is inversely proportional to the velocity. Click on each of the magnetic field, the 0.5B button, the B button, compare the radii of the circular paths. Answer. The radius of the circular path is inversely proportional to the velocity. If two particles of different charge but of the same mass move with the same velocity v perpendicular to the same uniform magnetic field, how would their paths differ? Click the Q button, then click the 2Q button. Summary. A charged particle entering a uniform magnetic field at right angles follows a circular path. The magnetic force on the charged particle provides the centripetal force QVB equals mv squared over r. Click the Show Label button to know the various parts of the apparatus. In the apparatus shown, ions from the source have negligible initial velocity. Click on the ion source and then drag the slider of the high voltage supply to increase the accelerating voltage V. Observe the motion of the ions from the source as the value of V is increased. Click on the ion source, then click the Calculation button to observe how the mass of the ion is calculated. Observe what happens when ions of the three isotopes of hydrogen, deuterium, tritium, are accelerated through the same potential difference V into the uniform magnetic field. Click on the button of the voltage supply to increase the value of the accelerating voltage V. Note the values of V when the collector detects ions. What can you deduce about the ratio of the masses of the ions? Summary. When an ion of mass m and charge q is accelerated through a potential difference v, its velocity v equals the square root of 2qv over m. When the ion moves with the velocity v perpendicular to the magnetic field of flux density B, mv squared over r equals qvb.